And what we're going to do is we're actually going to do, we're going to skip the first page of these notes for now. If we can get to them in class, we will. But I already have the front page of these notes recorded, and I think the front page is a little bit easier. So if we can't get to them in class, I might make this homework over the weekend. But we're going to do this one because this one is a little bit more challenging, and we definitely should do these ones in class. Okay, so today we're doing polynomial functions. We're finishing up the polynomials unit, and we're doing the word problems. And with the word problems, the math is not the difficult part, because for the math, we're actually going to use exactly what you were just doing on the worksheet. So in the worksheet, you were using the calculator to find x-intercepts, to find y-intercepts. You were using your calculator to find maxes and minimums, and that's exactly what we're going to be doing on this worksheet as well. We're going to be using the calculator to find specific points on the graph. The part that is more difficult about this is that we have to use the calculator to kind of interpret. We have to interpret the story problem and see which point is the answer. Is it an x-intercept? Is it a maximum? What point should we find? Okay, so the math for today is not difficult. The part that we are going to have to think about is like, what should I be finding on the calculator? Okay, so what I'm going to have you guys do first is they're talking in this about a piece of cardstock, and I don't know if you guys have ever worked with cardstock before, but it's this like thick paper. Have you guys ever used cardstock? Anybody? Okay, so we're going to draw a piece of cardstock, and it says that it measures 8 centimeters by 12 centimeters. So we're going to draw this piece of cardstock right here. And I'm going to show that it's 12 centimeters by 8 centimeters. And it says that what they've done is they cut a 1 centimeter square out of each corner. So we're going to cut a 1 centimeter square out of each corner. So I'm going to draw it like this just to show that I'm cutting it out and I'm making it disappear, throwing that 1 centimeter square away. So they're saying they're making an open box. That means it's a box with no lid. An open box with a rectangular base is made from a piece of cardstock. The cardstock is 8 by 12. And they're cutting out a square from each corner, and then they're turning up the sides. So what they have is we cut out 1 centimeter square from each corner, and then we folded this, and we folded this, and we folded all the sides. And then this makes a little box, and the little box does not have a lid. Does that make sense? You can kind of visualize it? Okay, this is a very common math problem, and it's common for Math 3, but it's also common for like Math 4, pre-calculus, calculus, the SAT, the ACT. They like to phrase the question like this. So you're going to see it for this class. You're definitely going to see it probably on the EOC, but you might also see it on other standardized tests for other classes. Okay, so this is a pretty common problem. We just want to not be intimidated if we see this wording again. Okay, so this is what they mean when they say cut out the corners and turn up the sides. All right, so if I had a width of 8 originally, and I cut off a 1 centimeter corner, and I cut off a 1 centimeter corner, and I folded the sides, my new width is not 8 centimeters. It's now 6 centimeters, right? I cut one, I made 6. So we're going to write width, and we're going to say it's 8 minus 1 centimeter minus 1 centimeter is 6 centimeters. And I do want you to write it exactly like this, because these are our notes, and this is going to help us to understand it in the future. We just want to be able to remember how this works. Okay? The length originally was 12. I cut off a 1 centimeter square. I cut off a 1 centimeter square. What is my new length? 12. It was 12 to start with? 10. So we said length was 12. We subtracted 1 from the right side. We subtracted 1 from the left side, and we have a new length of 10. Okay? Now this is the part that gets a little bit weird. So here's my corner, right? I have a 1 by 1 square. I fold up my little flaps, and what is the height of my box? It's 1. Whatever that square is, when I fold up my flaps, that square creates the height of my box. Everyone see how that works? So a 1 by 1 square makes a height of 1. Okay, does anyone remember the formula for volume? Yeah, length times width times height. So we're going to say that the volume, length times width times height, the volume of this particular box that we just created would be 10 times 6 times 1, which is 60. 60 centimeters cubed. Okay, what we just did was not a Math 3 problem. What we just did, because we had all the numbers, what we just did was like, I don't know, when do you learn volume for the first time? 6th grade? We just did a 6th grade math problem. Okay, are we comfortable with that? We can see length, width, height? Okay, let's try it again. This time they said they're going to cut out a bigger square. So we're starting with the same picture. We have 8 centimeters, we have 12 centimeters. We're cutting out a bigger square this time. I think my drawing is over-exaggerated, but you guys get the idea. So they cut out 1 centimeter last time, but we're cutting out something bigger here. Looks like that. So for our width, we originally had 8. But we cut off 2 centimeters and we cut off 2 centimeters. And so it's no longer 8. What is it now? 4. So for our width, we had 8. We cut off 2. We cut off 2. And that gave us 4. Okay? For our length, we had 12. We cut off 2. We cut off 2. And that gave us a length of 8. Okay? So we started with 12, we cut off 2, we cut off 2, that gave us a length of 8, okay? We had a 2 centimeter square, we folded up our sides, and so we have a height of 2. A height of 2. So for the volume, we're going to do length times width times height. And what are we going to get? 64 centimeters cubed. Okay? This is another 6th grade math problem. We plugged the numbers in, we got the volume. Does it make sense? Okay. We are going to turn this into a Math 3 problem. Okay? So again, we're going to draw this. And this time they're going to say, well, what happens if you don't know what size square you're cutting out from the corners? So if we don't know the size of the square, we're going to call the dimensions of the square x by x. Because that's what we do when we don't know something. We give it a variable. So we're going to call that square x by x. So I'm going to look back up here and I'm going to see how I created these dimensions in these 2 previous problems when I was doing the 6th grade math. Okay? So when I was doing the 6th grade math, I said that the width was 8 minus 1 centimeter minus 1 centimeter, or 8 minus 2 centimeters minus 2 centimeters. So if I don't know the dimensions of the square, I'm going to say 8 minus what? I'm going to say minus x minus 2x. Good correction. Okay, 8 minus 2x. Perfect. So that's the new width. My length should be what? 12 minus 2x. Very good. 12 minus 2x. Okay? And then my height should be what? Just x. Perfect. Okay? And this is how the problems always work out. So this is not just this specific example. This is how they always are. So if you do this for pre-calculus, if you take calculus and do this for calculus, if you do this for the SAT, for the ACT, the way that they write this question, the width is always going to be the width minus 2x. The length is always going to be the length minus 2x. The height is always going to be x. So you don't have to worry about the problem being different. It's always set up the same. Okay? All right, so now we're going to say our volume is going to be length times width times height. And like you suggested, Jen, we're going to put the x in the front, because whenever we have a plain x, we usually put those in the front. So length, width, height. And we don't need to multiply these out, because the final answer of what we're going to get today, the important part, is for us to be able to plug this in the calculator and then figure out how to interpret this in a real world context. We don't care so much about the equation. We don't care about the numbers. We care more about like how to interpret things. Okay. So what I'm going to do is I'm going to take this, I'm going to plug this into my calculator. X times 12 minus 2x times 8 minus 2x. And then I want to be able to see the entire graph on the window. And right now I don't know how big to make my window. So what I like to do is I like to look at the table and just see how big the values are for this graph. So what I'm going to do next is I'm not going to ask to graph it. I'm going to look at the table. So I'm going to hit second graph. X is the size of the square that we're cutting out. The output, if you cut out these size squares, the outputs are going to be the volume of your box. All right, so X is the size of the square that you're cutting out. Y is the volume of your box. And you can see here that the volume of your box, we've got 60, 64, 36. That tells us how big our window should be. Okay, so my X values 0 to 6, so my typical window that goes to 10 is going to be big enough, but my window that goes to 10 is not going to be big enough for my Y coordinates. I want my Y coordinates to be bigger than 64. So I'm going to hit the window button, and I'm going to go down to my Y max. My bigger Y values need to be bigger than 64. And what's a good number that's bigger than 64? Maybe 70. So you can do, I wouldn't do 65 because that's barely bigger than 64. That's going to barely be big enough. I usually do like a little bit bigger than the number so that I have some wiggle room. So I put in 70 there, and now I'm going to hit graph. And I should be able to see everything that I want to see. So I can see the whole graph. I'm not worried about this part down here because this part down here means that the volume is negative. Can boxes have a negative volume? No, that doesn't make sense. So for a word problem, these answers are not going to make sense anyway. Okay? How are you guys feeling about what we've done so far? So I plug the equation in. I look at the table to see how big my table should be. Okay, so before I go any further, I'm going to write down what my variables mean, just so that I won't forget. So X is the size of the cut out square. X is the size of the cut out square. That's what we're going to input into the equation, is how big that square is that you're cutting out. And then once you put it into the equation, the Y is going to be the volume of the box. The Y is going to be the volume of the box. So then when we go through and we answer the questions, we want to figure out if the question is asking for an X coordinate answer or if it's asking for a Y coordinate answer. Okay, and that's going to help us figure out what we should do on the calculator. So the first question says, what is the volume? If it's asking what is the volume, do they want a Y coordinate or an X coordinate? They want a Y coordinate, okay? What is the volume if a 1.25 centimeter square is cut out? So if they want the Y value, that means that they gave us an X value, okay? So for me to plug in any X value that I want, I'm going to hit second trace, and I'm going to go to option number 1. Second trace, option number 1 allows me to type in any X value that I want. Second trace, option number 1. Second trace, option number 1 lets me plug in any x value that I want. And I want to plug in 1.25. Okay, so I'm going to write this down, 1.25, comma, 65.313. This is not my answer, right? If somebody said, what is the volume if I get a 1.25 centimeter square cutout, and they said 1.25, comma, 65.313, I would think they were crazy and they didn't understand the question. All right, so I'm going to write a sentence for the answer. The volume, if a 1.25 centimeter square is cut out, is 65.313 centimeters cubed. Okay. The next question says, what is the volume? So what are they asking for? A y coordinate. What is the volume if a 2.3 centimeter square is cut out? So again, they gave me an x value of 2.3 to plug in. So I'm going to type in 2.3. If you still had that up on your screen, you can just type in a new x value, or you can do second trace all over again. Second trace number 1, type in 2.3. So I'm going to write this point down, 2.3, 57.868. Okay, so the volume, if a 2.3 centimeter square is cut out, is 57.868 centimeters cubed.
Would we get points off if we didn't write the unit like centimeters cubed?
It's a good habit to get into. If you consistently have terrible sentences, I will mark you down. If you have one sentence that's not great, I won't. In a testing situation, I do want to see a sentence, though. Yeah. The reason I have you guys do this here is because later on in math, interpreting the answers is important and it gets more difficult. So it's better for you to write good sentences now so that later on you're just good at writing sentences. And then when it is more difficult to interpret, that's not what you're working on. Then your sentences are already good enough. Yeah, that's the goal. All right, the next question. What is the volume if a 4.5 centimeter square is cut out? 4.5, what do we get? Does that make sense? So why would you get a negative volume if you try to cut out a 4.5 centimeter square? So because 4.5 times 2 is not 8, is 9. So the dimensions of the piece of cardstock was 8 by 12. If you cut out 4.5 from each side, then you're cutting out 9. You're cutting out more from the squares in the corners than you even have available to cut. Does that make sense? It's not even possible to cut out a square that big. So we're going to say it's not possible to cut out 4.5 centimeter squares. And we can write, it was 4.5, negative 13.5, I think. Okay. When you're done writing that sentence, go ahead and flip the page. Okay, this has a couple questions, but the first question says, for what size square? So are we finding an x or are we finding a y? An x. We're finding an x. For what size square is the volume the largest? Okay, we're finding an x. For what size square is the volume the largest? Where are we going to look on the graph? We're going to look at the maximum, okay? So I want to find that point up there. I'm going to look 1, 2, 3, 4. I'm going to look between 0 and 4. Are you guys comfortable with that? Does that seem like a good place for the maximum? So I'm going to do second trace, option number 4, and I'm going to look between 0 and 4 for the maximum. I always ignore the guess because it's always silly. Okay, so the maximum, let me write down what I did here. So I did second trace number 4. Okay, and my point is 1.569, but it's followed by a 5. So 569 would round to what? 570, okay. 1.570 and then 67.604. Okay, so a 1.570 centimeters square would create the largest volume. Okay, we answered the first question. Okay, the second question, now make sure, does everyone still have this on their screen? Because I'm going to show you a calculator trick. Everyone still have this up? Yes? Okay. It says, what are the dimensions of the box with the largest volume? What does the word dimension mean? Like in this context, what does dimension mean? Side. Like what are the specific words they use for side in this context? Length, width, height. Okay, so let's write this down. Length, width, height. Length, width, height. Okay, so they're asking what's the length, what's the width, what's the height of the box. So let's go back. The formulas that we're using in this particular problem for the length, the width, and the height is 8 minus 2x, 12 minus 2x, and just x, okay? So the trick that I have to show you is that in here, anytime you're doing anything on your calculator where you're finding an x, you're finding a y, x-intercept, max, min, if you have pulled up a point on your calculator screen, your calculator momentarily stores that number for you. Okay, so what we're going to do is we're going to get out of this screen. We're going to hit second quit to get out of the screen, second quit. And what I want everyone to do is hit the X button. Hit the X button right here. And if you press enter, you'll see the same decimal as the X coordinate that was just on your screen. Because what your calculator has been doing this entire time is it has been momentarily storing all these numbers for you, just in case you wanted to use them. So we're going to use this X value that our calculator was storing, and that way we don't have to worry about rounding decimals early on in a problem. Because at this level of math, we should never do a computation with a rounded number. We should always use the perfect number, okay? So I'm going to say that my width is 8 minus 2x. There's my width. 12 minus 2x is my length. And then plain old x is my height. And here are my 3 dimensions. All right, so go ahead and plug those in. So 8 minus 2x is my width, 12 minus 2x is my length, and x is my height. So I have my 3 dimensions written down, just x. And since I want my notes to be good, so I'm going to write my notes down. I'm going to write 8 minus 2 times 1.570. This is what my calculator is doing for me. 12 minus 2 times 1.570. And then x is just 1.570. So we have width, length, height. So the dimensions of the box with the largest volume are 4.861 centimeters by 8.861 centimeters by 1.570 centimeters. And you can actually do it with the y-coordinate too. We didn't need the y-coordinate, but your calculator did store it for you. You have to look at the green letters. So the green letter y is the 1. So if you hit alpha 1, the y value, and press enter, the y value that we had, the 67, that's also stored in your calculator as well if you needed it for something. We don't, but it's there. Okay. All right, last question to answer. What is the largest volume? What's the answer to that? What was the largest volume? Okay, the largest volume is 67.604 centimeters cubed. Okay. All right, how do I feel about finding those? Were we comfortable with all of that? All right, the next question says, what size square? We're trying to find an x value. Okay, what size square could be cut out that would give a volume of 50 centimeters cubed? What size square, so what x value would be cut out that would give a volume of 50 centimeters cubed? So they're asking us what x value would give you a y value of 50. So the only place on our calculator that gives us y values that can give us an output is the y equals. So what we're going to do is we're going to hit y equals, and we're going to go down to y2, and we're going to plug in 50. And what that's going to do is it's going to make a horizontal line across the screen where the volumes of 50 are happening. Okay, so go ahead and graph that. And you can see there's a volume of 50 right here, and there's a volume of 50 right here. And then we have the negative volumes, and then we have another volume of 50. So none of these volumes are going to make sense for this problem. So all these we're going to ignore, but these two answers we're going to think about. These two answers are going to make sense. So for this one, I'm not going to have you guys write the sentences because it ends up being a lot of sentences, but we have to figure out what this point is. So it's going to be a size of a square and a volume of 50. And we're going to do second trace, and we're going to find the intersection of the curve and the 50 line. So we're going to do second trace, option number 5. And for the first intersection, you don't have to do anything here. You just have to press enter, enter, enter. And it should give you that first one. Everyone do that? Second trace, option number 5, enter, enter, enter. So second trace, option number 5, enter, enter, enter. And the first one has an x coordinate of 0.723. and a y coordinate of 50. And they want us to write the dimensions. So how are we going to find the dimensions? Dimensions are length, width, and height. How do we find the dimensions? So we're going to do quit to get out of this. We have the x coordinate, the x value stored that decimal. And what do we do with that? So we have 8 minus 2x is going to plug in the 0.723 for the x. 12 minus 2x is going to plug in the 0.723 for the x. And then the height is just x. So we just have to type all of these in with that decimal. So 8 minus 2x, 12 minus 2x, and then just x. And there is our width, length, and height. So 6.554, 10.554, and 0.723, and then all of these are centimeters. Okay, how do I find my second answer? So I just did this one. What should I do now? So I'm going to do second trace. I'm going to go back to option number 5. And then this time, all I have to do is I have to move the cursor closer to the second intersection than it is to the first. So I'm just going to hold down my right arrow until I'm closer to this one. You don't have to be on it. You just have to be near it. And then I'm going to press enter, enter, enter again. And then it will just find the other one instead of the first one. So now I've got 2.584, comma 50. And now if I do second quit to get out of this one, now if I type in x, it will have the new number stored. And so I can type in these formulas all over again to get my width, length, and height. So 8 minus 2x, 12 minus 2x, and x. So there's my new dimensions. And these are all centimeters. Does that make sense to you guys? So we can see we had two options that would give us the exact same volume. We have a smaller square that would give us a volume of 50. We have a bigger square that would give us a volume of 50. If you wanted to cut out something, so if we were to make these boxes, what do you guys think is happening with the little squares? You cut out the square, you make the box, you have all these little cutout squares. What do you think that the company making the boxes is probably doing with all those little squares? Maybe reusing them. What do you think they're reusing them for? More boxes, maybe. In all likelihood in America, what are they probably doing? They're probably throwing them away. Okay, so if you had these two options, and you wanted to minimize the amount of waste you were making, which option would you go with? If you wanted to minimize the amount of waste. The 0.723. I'd go with this one if I wanted to minimize waste. Why? It's a smaller square. It's the same volume. I'm going to have the same volume box, but I'm going to be cutting out smaller squares, which means I'm going to be throwing away less as I make my box. Does that make sense? Okay, so the next question says, what size square could be cut out where you'd get a volume of 46, but you're minimizing waste? So this problem essentially looks exactly the same. We're going to go to 50, but we're going to say a 46 cubic centimeter box. But when we graph it this time, they don't want us to look at both options. Which option do they want us to look at? The first one. They want us to look at the one that has the smaller square. If you're minimizing waste, you're cutting out a smaller square because they're probably taking the squares and throwing them away. They could be using them, but they're probably not. Okay, so when they say what minimizes waste, it's just telling you, I don't want both answers, I only want this answer. Okay, so let's look at that first one to minimize waste. We're going to do second trace, option number 5, enter, enter, enter. Okay, so there's my point, 0.638. And then we're going to do the same thing we did before. So I'm going to quit out of that, and then I'm going to type 8 minus 2x, 12 minus 2x, and x. Okay.